Hello, my people. Hope we're doing well. Another installment of optimization. Yay! All right, let's jump right in. You're designing a rectangular poster to contain 50 inches squared of printing with a 4-inch margin at the top and bottom and a 2-inch margin at each side. What overall dimensions will minimize the amount of paper used? Okay. So I'm going to do this in pencil so I don't smudge everything. Okay, so we have a poster, and then we have the area, the printed area inside of it. There we go. And so something like that, and something like that. Now the upper and lower margins, they said, were larger. Okay, now it's obviously not to scale, but you know, good enough. So from here to here is 4, and from here to here is 4. Over here is 2, and over here is 2, and inside here I have 50 inches squared of printed area. Now I need to go ahead and designate variables. Now, what I'm trying to do is I'm minimizing the amount of paper. So I'm minimizing area, really. Now, one of the equations is going to be the area of the whole thing. The other one is going to be the area of the printed. Well, the area of the printed is the one that has the actual value. So that's the one I'm going to use as substitution. So that means it's probably a good idea to designate this inner area, the dimensions of the inner area, the area of the printed area, with x and y, and then of course you can from there extrapolate out and call this y plus 4, and you can call this x plus 4 and y plus 8. Okay. Now you could have done it the other way around. It just makes the substitution equation much more difficult. I don't recommend it. So we know that xy is equal to 50. That means y is equal to 50 over x. Now, the area that I'm trying to minimize is, of course, the area of the entire poster, but that's of 3 variables, a being in terms of 2 variables. Too many variables, and so that's where the substitution comes in. That means that I have a of x is equal to x plus 4, and this becomes 50 over x plus 8. Well, before I differentiate, it's probably going to be a better idea to go ahead and get it all multiplied out and simplified and sort of, you know, term by term kind of thing. So let's go ahead. The first is obviously going to be 50. All right, the outer is going to be 8x, the inner is going to be 200 over x, and the last is going to be 32, which means my a of x is 8x plus 200x to the minus 1 plus 82. That differentiates rather simply. It's 8 minus 200x to the negative 2. Now when I set this equal to 0, I'm going to go ahead and push the 200 x to the negative 2 to the other side. I'm going to get basically 8x squared is equal to 200. Now you could do it as sort of the difference of 2 squares on the other side, because once you divide through by 8, you're going to get x squared is equal to 25. But you're not going to be entertaining the negative anyway, right? You're simply going to be entertaining the positive. And of course, if x is equal to 5, then y is equal to 10. So the dimensions of the poster should be, and we're going to do obviously the x plus 4, 9 by 18. Okay, because it's going to be 5 plus 4, and then the 10 plus 8. And that is going to minimize the amount of area, the amount of paper used. And of course, that's the same thing as the area being minimized, the total area. Now this one is a little bit more difficult, but it is one of those ones that pops up in just about every book The only difference between them is the fact that the width of the hallways is different. Okay. Now it says 2 corridors, 3 feet and 4 feet wide respectively, meet at a right angle. Okay. So, boom. Find the length of the longest non-bendable rod that can be carried horizontally around the corner, as shown in the figure. Disregard the thickness of the rod. Okay. Now, here's the thing. We're optimizing, but you need to remember that the longest rod is not just longest in general, but the longest rod that can actually navigate that turn. So the longest rod is going to be the shortest hypotenuse of any triangle that can be made right here. Okay. So the shortest hypotenuse is, and of course anything shorter than the shortest hypotenuse will also go around the corner. Okay. So what we need to do is we need to basically start carving this up. Okay. So we'll go ahead and we'll extend this line to here, and we'll extend this line to here. That is obviously 3. That is obviously 4. Let's go ahead and designate this as x. Let's go ahead and designate this as y. Now I know I need to figure out a way to represent the entire length right here. Okay. Now, basically what happens is this right here is x plus 3. This right here is y plus 4. So, I guess you could say that the length is equal to, the square root of x plus 3 squared plus y plus 4 squared, and you could try and figure it out from there. That's not how we're going to do it, okay? The fact that there's a theta right here ought to give you an indication, okay? So what we want is we want a theta value that is going to minimize this. And then, of course, we can use that theta value to figure out what that value is, right? And that's the only way you can ensure that it's still a straight line when it goes around the corner, right? So what we need to do is let's go ahead and designate this as length 1 and this as length 2. If you haven't noticed, you have right triangles in here. And you need to basically the length to be in terms of theta. And they gave you that hint by actually putting theta in the whole schematic. Okay. Now, I know that for this lower triangle, I want to find something to represent L1 in terms of theta, and I want to use the constant because I don't want to increase the number of variables, right? So this is opposite, this is hypotenuse, so I have sine of theta is opposite over hypotenuse. Now the relationship is different up here on the smaller triangle because it's going to be cosine of theta in order to use the constant right here of 3 over L2. Now that means L1 is equal to 4 over sine theta and L2 is equal to 3 over cosine theta. Now we're going to transform those into cosecant and secant respectively. And so now I have the length as a function of theta, and it's 4 cosecant theta plus 3 secant theta. Now, you think that this is going to get messy, but actually it doesn't get too messy. When you differentiate, you certainly get negative 4 cosecant theta cotangent theta plus 3 secant theta tangent theta. But when you turn all of that into sine and cosine, okay, what you're going to get is you're going to get negative 4 cosine theta over sine squared theta, right? Because this is 1 over sine, this is cosine over sine. Here we're going to have 3 sine theta over cosine theta. Now, it's not as easy to do it, but let's go ahead and scratch this out, turn that positive, and just turn it into the proportion so I can actually save a little bit of room. By the way, this is cosine squared in the denominator. When I cross multiply, I get 4 cosine cubed theta is equal to 3 sine cubed theta, And you're thinking, gosh, this is just getting worse, except for the fact that you can divide both sides by cosine cubed and both sides by 3, and you get 4/3 is equal to tangent cubed theta. Okay, well, that means that tangent of theta is equal to the cube root of 4/3, which I'm not going to keep you in suspense, gives you a theta value, if you're looking for it in terms of degrees, of 47.743 degrees. Okay, now, if you're using degrees, that's fine. In this gives you an idea of how big it is. It's probably more efficient to use it in terms of, so that's degrees. In radians, it's 0.833. And if I actually evaluate this at that value, it's going to come out to 9.866 feet. So the longest, what do they call it, a rod? Yeah, the longest rod is 9.866 feet. And done. Okay. Now, what we're going to do next is another trig problem, and it's going to look rather daunting as well, but it actually winds up being not that bad. Not that bad, meaning that there's not a whole lot of arithmetic that's in it. I mean, I think the worst ones are the ones that go onto the second and third page because there's so much cleaning up to do in terms of like radicals and derivatives of radicals and stuff like this. This is actually not too many steps. The difficulty, of course, is in setting it up. This one reads, a picture 4 meters in height is hung on the wall. So think of like you're at the museum and there's a painting on the wall. 4 meters is a really tall painting, but whatever. Picture 4 meters in height is hung on the wall with the lower edge 3 meters above the level of an observer's eye. So let's go ahead. Here's the wall. All right, and then we'll sort of draw someone back here, a museum patron. Now, if he looks straight at the wall, basically that is eye level. Okay, so that's eye level. And it says that the lower edge is 3 meters above. So this is not going to be to scale. Let's say that this is the lower edge of the painting. That's the upper edge of the painting. That means that this right here is 3 meters. And this right here is 4 meters. Now, that's basically, we've made sense out of the first sentence. A picture 4 meters in height is hung on the wall with the lower edge 3 meters above the level of an observer's eye. The question it's asking is, how far from the wall should the observer stand in order to obtain the most favorable view? Meaning that the picture should have basically the angle from the person's eyes to the bottom of the painting to the top of the painting. We're going to maximize the angle. Okay, well, let's go ahead and let's draw that angle, right? And so the angle looks something like this. And let's call it theta. So if this right here is theta, we're trying to maximize that. Well, think about the implications of what that means. What we're maximizing is always the output variable. So theta needs to be the output variable. But here's the thing, theta is not part of a right triangle, though we do have two right triangles. Here's the base, and here's the hypotenuse of the first one, and then here's the base, and here's the hypotenuse of the second one. So what's going to happen here is we're going to go ahead and label this one alpha, and this one beta, and we see the fact that theta is equal to beta minus alpha. Now that's going to be helpful because I can actually set up a trigonometric expression for both beta and alpha. Okay, I have something that represents this leg of the triangle, and I have a numerical leg over here of 3, and then on the longer one, remember it's going to be the sum of those two, so it's 7. So let's look at the smaller triangle. Tangent of alpha is 3 over x. Tangent of beta, the larger triangle, is 7 over x. But I need alpha and beta by themselves, so it's alpha is equal to arctan of 3 over x, and beta is equal to arctan of 7 over x. Now, you're going to be taking the derivative of arctan, and that's not too bad, except for the fact that you have reciprocal functions in the argument for those inverse trig. But let's go ahead and set it up. Since I know that theta is equal to beta minus alpha, I know that theta in terms of x is arctan of 7 over x minus arctan of 3 over x. Okay, now when I take the derivative of this, and it's really kind of interesting to be taking the derivative of theta, right, with respect to x. What I get is, remember, in the denominator, it's 1 plus whatever this is squared. And then in the numerator, it's whatever this is, you take the derivative of it. So it's negative 7 over x squared. And it's the same pattern over here. Since it's basically the only difference between this one and that one is the 7 and the 3, it's not like you have to figure out two separate really difficult derivatives. One is basically the same form as the other. Okay. Now that we have those, here's the tricky part. You need to remember that this is not a 7, it's a 49, because you get going fast and you're gonna label that as a 7. But that's a 7 squared. And if you need to go ahead and actually do that arithmetic in order to ensure that you don't make that mistake, by the way, those two negatives cancel, then do so. And you get 1 plus 9 over x squared down here. Now that's important because I want to simplify these, and I'm going to multiply both of them by x squared over x squared. And when I do that, I'm going to get negative 7 over x squared plus 49 plus 3 over x squared plus 9. Now, I'm going to be setting that equal to 0, so really what I have is a proportion. And when I actually do that, do the cross multiplication, and we're going to start back over here, I get 7, and then that's going to be x squared plus 7 times 9, which is 63, is equal to 3x squared, and 3 times 49 is 3 times 50 minus 3, so it's going to be 147. And then if I basically get it all to one side, it's going to be 4x squared minus 84, or x squared minus 21. Now, it's not all nice and clean, but you know that x is going to be equal to plus or minus root 21. And root 21, you're not going to be dealing with the negative of it, so basically you're going to be the positive root 21, and root 21 is approximately 4.583. And that's it. That is the x value, which makes theta a maximum. So the person should stand 4.583 meters from the wall. And we're done. And that's it. Now, if you have any questions, as always, shoot me an email. This last one right here, though, is a little less common than the other ones. I mean, the one with the pipe going around the corner. I mean, most books have something like this. Sometimes it's a painting on a wall. Sometimes it's the Statue of Liberty and the person's on a boat or whatever. But the more different varieties of these problems that I show you, the more likely that the overarching logic and the procedures that flow forth from that logic will sort of sink in. So I hope that was helpful. Like I said, if you have any questions, shoot me an email. Bye.